We are now moving into section 5.2. Remember, chapter 5 is on integrals. Section 5.2, we're going to talk about something called sigma notation, and then we're going to take some limits from finite sums. I'm going to let the number of rectangles go to infinity, what we were just talking about. But before we do that, we need to understand this sigma notation. So this kind of is a little bit of a diversion into what's called sigma notation. So when you see something like this, eventually I need you to be able to recognize what this means. So this capital Greek letter S, called sigma, that's why we call this sigma notation. And then A sub k here just is a general representation of some formula for the kth term, all right, some formula. And then k equals 1 to n means I plug in k equals 1, I see what that value is, I add to that, plugging in k equals 2, see what that value is, I add to that, plugging in k equals 3, see what that value is, all the way up to k equals n, whatever the stopping point is, n. Okay, again, a little foreshadowing, we're going to let this n go to infinity eventually because that will add up the areas of rectangles. But anyways, let's just make sure we understand sigma notation here in example 78. So let's say I have sigma of k as k goes from 1 to 5. That means, so here's my formula, this k. This k equals 1 was my lower index, 5 is my upper index. Okay, so we want to step from 1 to 5 by 1. So first of all, I plug in k equals 1 into k, I get 1. Then I add to that, plug in k equals 2 into k, I get 2. Then I add to that, plug in k equals 3 to k, I get 3. Then I add to that, plug in k equals 4 to get 4. Then I plug in k equals 5 to get 5, and that's a stopping point. And then I can actually add them up. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. All right? A little bit more complicated formula. So this was the simplest formula of all, right? K. So a little more complicated formula. I have minus 1 to the power k times k. And I'm going to step that from k equals 1, the lower index, to the upper index of 3. So I start at 1, and I go to 3, adding 1. So starting at 1, I plug in k equals 1. I get minus 1 to the 1 power, that's minus 1, times 1. That gives me minus 1. Plug in k equals 2. Minus 1 squared is 1 times 2. So plus 2. Plug in k equals 3. Minus 1 cubed times 3. So minus 1 times 3 is minus 3. Then I'm done. I'm at my I'm at my upper index, so I plug in, I just add these, sorry. Minus 1 plus 2 is 1, minus 3 is minus 2. Okay, a little more complicated formula. I'm only going to go from k equals 1 to 2 because I'm just trying to show you how this works again, but from k equals 1 to 2. So first of all, I plug in k equals 1. I get 1 over 1 plus 1, so 1 over 2. That's 1/2. Plus, add to that, plugging in when k equals 2, which would be my next one, which also is my last one. Because my upper index, so I get 2 over 2 plus 1, or 2 over 3, so plus 2/3. So then I would have to add these two together, common denominator 6, so 3 6 plus 4 6 is 7 6. All right, now, k doesn't always have to start at 1. This is the starting index, this is the ending index. So in this case, I'm actually going to start k at 4. Here's my formula, my a sub k is k squared over k minus 1. When I plug in k equals 4, I get 16 over 3. So there's my first term. Plus, when I plug in k equals 5, I get 25 over 4. 25 over 4. And then that's it, because I only wanted to go from 4 to 5. So now I add these together. Common denominator is 12, so I get 123/12.